welcome to the Optech Club at Bitshala. Here we uh, look into the Bitcoin Optech newsletter and try to understand the latest and cutting edge stuffs going on in Bitcoin. So today we will have a look at newsletter number 355. I have picked three noteworthy items from the newsletter so that we can have a look at it and try to understand the tech behind it. So, first one is a news item. And the news item is that Cake Wallet has added support for Payjoin version 2. So we'll have a look at what Payjoin is and how Payjoin has evolved over different versions and why is it important. So basically, Payjoins are 2% collaborative transactions. Uh, so what it does is that it enables the payer and the payee to construct the transaction in a collaborative fashion. So the normal or standard or vanilla way of constructing a transaction is that you have an address of the payee and the payer constructs the transaction to send Bitcoin or sats to the payee. So that is the general way of constructing a transaction, and there is no collaboration or interaction between the payer and the payee, except for the fact that the payee, gives his address. This has this standard way of transaction has a few pitfalls associated with it. One is the common input ownership heuristic. So if we assume that all transactions are constructed in the standard fashion, that means all inputs that go into a transactions will typically belong to the same entity. That is the payee. So you can assume or deduce this heuristic from the standard way of transaction. And the second heuristic or assumption that you can deduce from a standard way of constructing a transaction is that the change output identification. So if we assume that all inputs are spending UTXOs from the same script pub key type, for example, it could be a pay to witness public key hash or it could be a pay to public key hash. So if all inputs are spending UTXOs from the same type of script pub key, then we can reasonably come to the conclusion that the change is also likely to have the same script pub key type. So this is called as the change output identification heuristic. So for example, if you have an input of say pay to public key hash type, the let's say you have two UTXOs and then you are making a payment and the output or the payee is receiving it in a pay to script hash type output. And the change will be in pay to PKH type. That is, your input and the change will be of the same address type. The output can be of any address type. So if you look at the mempool and if you observe this kind of a transaction, then you can identify what is the output and what is the actual payment that is being done. So this is another pitfall of standard way of constructing a transaction. Then the third way of third pitfall in a standard way of constructing transaction is change identification from round amounts. If, for example, if you do a transaction and and at the output side, one is one UTXO is of round amount and the other is of some random amount. So you can now safely come to a conclusion that, or you can confidently come to a conclusion that the round amount is most likely to be the amount that you paid to the payee, and whatever leftover or a small portion of it that comes back, you can safely assume it to be the change amount. So these kinds of you can confidently arrive at these kinds of deductions from a standard way of constructing transactions. So in order to like mess this or reduce the confidence in these types of heuristics, we can use a protocol called as Payjoin. Uh, so basically, the workflow of a Payjoin I have shown here. Um, so you have the network that keeps churning out blocks every 10 minutes. So you have a sender and receiver. As I said earlier, PageJoin is a collaborative transaction. This is a V1 PageJoin transaction, that is version 1. So what the receiver does is that the receiver announces or advertises to the sender that pay me at this address and use this endpoint to communicate with me. So the receiver basically sends this information across to the sender. Once the sender receives this information, what he does is that he constructs a partially signed Bitcoin transaction, a PSBT. It has his inputs and has some blanks so that the receiver can fill in the inputs, and the sender sends this PSBT across back to the receiver. So what the receiver does is that the receiver puts in his inputs further and then passes back the final PSBT to the sender. Now the sender validates the PSBT, adds his signature, and then broadcasts the transaction. So basically, what happens here is, let's say the sender wants to send 1 Bitcoin to the receiver. How he does is that the sender probably puts in 1.5 Bitcoin, and the receiver also puts in some, let's say, 0.2 Bitcoin, and the transaction is constructed in such a fashion that the sender pays 1.2 and the receiver pays 0.8, and the total along with the change that goes back to the sender and receiver amounts to 1 Bitcoin that the receiver needs. So basically what happens here is that the sender and the receiver collaborate. It's not just the sender has all the inputs and the receiver has all the outputs. Both the sender and receiver will have inputs. Both the sender and receiver will have outputs. So this basically obfuscates the common input heuristics. So if we do this exercise, you can no longer be sure that all the inputs are from the sender and all the outputs except for the change are to the receiver. So this heuristic or conclusion gets messed up if you do this kind of a transaction. So this is a PageJoin transaction. This is V1. The problem with this PageJoin V1 transaction is that it requires the receiver to always have a server online so that he can advertise or announce his address and his server details. And it has to be synchronous. So all this back and forth communication has to happen synchronously, and finally the PSBT has to be finalized by the sender and broadcast. So till this whole sequence gets completed, the transaction is not final, and you can't expect a stable or a successful transaction until all the 5 steps are completed. So it has to be synchronous. That is a drawback. The third drawback is that when you send the pay, so here you can see that once this communication is done, the sender sends back a PSBT to the receiver. So this communication happens over vanilla HTTP protocol. So this exposes the whole protocol to man in the middle kind of attacks. This is a drawback in the Payjoin V1 version. So to address all these things, Payjoin V2 is being proposed, and it exists as a BIP, and the number is 77. Similarly, Payjoin 1 also exists as a BIP. Its number is 78. So what happens in V2 is that in between the sender and the receiver, there is a untrusted third party called as the directory. So what this does is that it temporarily stores the PSBETs and the endpoint informations. So what this enables is that the protocol can become asynchronous, and there is no need for the sender and receiver to sequentially communicate and then finalize the transaction and then broadcast it. So here communication can happen asynchronously. As with the page V1, the receiver advertises his Bitcoin address and the Payjoin endpoint. So this endpoint and address is basically stored in this directory. The sender can fetch what he is looking for from this directory. Once he gets the information like the address and the endpoint, he can construct the PSBT as in the V1 version, and then he can pass this PSBT to the directory. He doesn't have direct communication to the receiver, and once he passes this PSBT on to the directory, the PSBT stays there in the directory. Now the receiver can retrieve whenever he wants. He can retrieve this PSBT, decrypt it, validate it, and he can add his own inputs and adjust the outputs and fees, and then encrypt the whole PSBT as a OH TTP using OH TTP protocol. That is oblivious HTTP protocol. So this step adds safety or adds privacy to the communication as opposed to V1 where this was done over vanilla or plain HTTP. So once this is done, the receiver then uploads the PSBT to the directory. In the meantime, the sender keeps polling this directory for new messages with respect to the transaction that he tried to construct. So he keeps on polling, and once the receiver puts this updated PSBT into the directory and he polls, he will get a response. So once he fetches the response, he then validates it and then publishes it to the network. So this is Payjoin V2 version V2. So basically, what it improves upon V1 is that it makes the protocol asynchronous, and it introduces a secure element or layer using oblivious HTTP protocol. So basically, this makes it much more robust and prevents man-in-the-middle attacks that Payjoin V1 was susceptible to. So now this is the workflow of Payjoin V2. So this is what this is what new Cake Wallet has added as a support. So that is the news, and I hope we get to understand Payjoin V2. So basically, Payjoin V2 is now it is clearly defined as a BIP, and it is up to the wallets to adoption, and and once there is sufficient wallet adoption, I think the protocol will be of much more use. So it all that it does is that it messes up chain analysis. So chain analysis is basically based upon heuristics, and if there is sufficient adoption of Payjoin V2, we can be we can like discredit chain analysis heuristics much more effectively. So I'll stop here. If anyone has any questions, I can wait for a few minutes. Otherwise, I'll move on to the next news item. Okay. Uh, the next news item is Sparrow wallet has added support for pay to anchor transactions. So let's have an understanding about what pay to anchor transactions are. Okay, um, basically we'll have to understand understand the uh, understand the issues associated. So basically, pay to anchor outputs are tiny. Anyone can spend witness outputs. So they serve these sort of outputs are primarily introduced or designed so that they can serve as an anchor for fee sponsorship schemes such as ephemeral anchors. Basically, they are being developed or thought about in order to improve the performance of Lightning transactions. Um, So, in order to understand pay to anchor, pay to anchor transactions or outputs, we need to have some understanding about V3 transaction relay policies. So, uh, while constructing a transaction, you will put the first field in any raw transaction is its version number. Uh, this is a new version number that is being developed or that is being brought in because when you signal a transaction to be a version 3, a special set of rules a special set of rules apply for V3 transactions. Uh, version 3 transactions are a set of opt-in mempool policies. What it does is that it sort of applies a special set of rules on top of existing mempool policies. So these are required or brought in order to prevent or mitigate transaction pinning attacks. So transaction pinning attacks are nothing but uh, are nothing but situations that can arise where you have a parent-child transactions in the mempool, and there is an attacker who wants to prevent the parent transaction from getting mined. So he wants to prevent or make it prohibitively expensive for the parent transaction to be mined. So what he does is that the attacker constructs a child transaction that spends an output from the parent. But he does it in a fashion such that the so he does it in a fashion such that the child that he constructed is bloated in size and it pays a very low fee rate. Uh, he constructs this child transaction and then he broadcasts it. So now if a parent is sort of trying to RBF his own transaction, now he has to pay for the fees, cumulative fee. He has to pay a replacement fee that is more than the cumulative or combined fee of the parent and the child. Remember that the child has been is not a genuine transaction. It's a malicious transaction that has been put in place only to make it prohibitively expensive for the parent. So this is how a pinning happens. There are other types of pinnings, witness mutation, and anyone can pay pinning. So the basic idea is that an attacker tries to make a transaction prohibitively expensive. So that is transaction pinning. So these V3 transaction relay policies are being developed or put up in order to prevent these kinds of attacks and to improve the fee bumping reliability. So basically, what happens is that when you set the version number of your transaction to be 3, you are basically requesting the nodes to apply V3 policy treatment to that particular transaction. So these these new special set of policy rules that apply to these transactions are called as topologically restricted until confirmation rules or truck rules. So you might have, or you will likely come across terms like truck transactions. So basically, these are there are a set of some 8 rules that apply to these transaction to this V3 transaction. So if you set the version to be 3, you are signaling that truck policy rules will apply on top of standard relay rules. And then you also say that when the version is 3, it also means that even though your transaction doesn't signal for RBF via the n sequence value, even though if it doesn't signal it by default, if your transactions version number is 3, that means this transaction can be RBF, that is, it can be replaced by fee. So these are the first 2 conditions. Then any unconfirmed ancestor or descendant, if you are trying to add a descendant to your to a truck transaction, that new transaction must also signal for truck rules. That is, it should also have a version number of 3. So that is another rule. Then any unconfirmed truck transaction can't have more than one unconfirmed ancestor or more than one unconfirmed descendant in the mempool. So this is a very important rule. So this is SIGOP adjusted V size must not exceed 10,000 V bytes. So this is another important restriction that you place on a truck transaction. So this is done to avoid attacker from adding a descendant or child transaction which is bloated and is meant to make replacement by fee for the parent prohibitively expensive. So because now we are putting in 10,000 V byte limit on the truck transaction, so the attacker cannot add such bloated malicious transactions. Another thing is that if there are any unconfirmed ancestors, the ancestors size should not exceed 1,000 V bytes. So this is also related to the issue of attacker bloating it. So we are minimizing the attack surface in truck rules. Also, a standalone truck transaction may be relayed below the mempool's minimum fee rate policy, provided there is a provided the whole package of the truck transaction, that is its ancestor and descendants have a fee that is have a fee total fee that meets the aggregate fee requirement. So these are all basically the rules that truck transactions have. So how is this related to how is this related to pay to anchor? So pay to anchors are basically truck transactions. So they cannot be a normal transaction. When you construct a pay to anchor transaction, you have to specify its version to be 3. The fact is that we'll first look at the problem and the solution that pay to anchor transactions offer. So typically in a lightning transaction, when you open a channel with a channel partner, you have to agree on a specific fee for each commitment transaction. This depends upon the mempool's condition during the time of commitment. So, and because the fee rates are highly variable, and you cannot predict the fee rate with like with a lot of confidence into the future. Typically, you have to overestimate the fee, and you have to have some cushion for a fee rate spike. So, if you don't allow for that provision, the chances are that your commitment transaction, if you want to exit and you want to close, or if you want to publish your commitment transaction, it might not get through the mempool. So that's why we have to provide a buffer for this for fee rate spikes. So this typically weighs collateral, like you are spending more sats or committing more sats to this commitment transaction rather than using it for channel balances. So, to in order to prevent this, so the problem is that you cannot estimate the mempool's fee rate in advance, and you have to keep sufficient balances for fee rate spikes. Now, pay to anchor is a solution that does not force you to choose a fee rate while creating the commitment transaction. So here, this is where the pay to anchors contribute towards efficient lightning channel management. So when creating the commitment transaction, you don't necessarily have to fix a specific fee rate, or you don't have to provide a buffer anticipating fee rate spikes. Here you can use a pay to anchor transaction as a commitment transaction. So what you do is that you put in version number 3, and you mark the segwit flag as 1. Uh, then you can add your inputs. Uh, the specificity of the pay to anchor transaction comes in the output part. So you don't typically have to specify an output with the exact amount that you want out of the commitment transaction, and you can you can just put in a nominal amount which is above the dust limit. And in the script pub key, you typically put a put an always true condition. Like there is no key requirements, that like there is no public key that is required to satisfy this script pub key. So this is basically a kind of a open-ended transaction. You can use this open transaction to you can like treat this as a parent and add a child to it, so that you can replace this transaction in the future. So that is so basically P2As are basically dummy transactions that you put in place and publish to the network. Now, when you want to when you want to close, or when you want to actually actuate this transaction, you can always add a you can always add a you can always create a child base for parent and spend it. You can add sufficient sats that you require based upon the fee condition, and you can push this transaction into the block. So this is basically the idea behind a pay to transaction. So pay to anchor transactions are zero fee paying transaction that any party can bump by spending the anchor and adding fees. So the idea is you put in a dummy transaction, and then you bump it when required. This is the concept behind pay to anchors, and Sparrow Wallet has added support for this transaction. So this is important because you can use Sparrow Wallet to create these pay to anchor transactions. So it basically takes care of all the script upkey part, and also you can RBF it or CPFP it after. You can RBA for CPF it after whenever you need. So you can do all management using Sparrow wallet. So this is about pay to anchors. I'll wait a few minutes for questions. If not, I'll proceed to the next item. Okay, cool. So the next item in our that we'll be having a look at is clustered mempools, and they have introduced some code changes in Bitcoin Core to enhance or to facilitate effective cluster mempool operations. So we'll basically have a look at what cluster mempools are, and then have a look at what new functions that has been added to Bitcoin Core. So, basically, cluster mempools are a redesign of mempools as we have it in Bitcoin right now. Um So what it does is that instead of having transactions float around in the mempool like without any relation to each other, cluster mempool design is a way to organize transactions that are floating around, related transactions that are floating around in the mempool, and you sort of add some sorting logic to these groups based upon their fee rate. So this is the whole idea behind cluster mempool. So why cluster mempool idea is being worked upon? So now there are like now there are policies that govern what transactions go into a block. So miners do that, and there are policies that manage the transaction that live inside a mempool. Because mempools are set to default limit of 300 MB of RAM, you cannot keep on adding transactions that come that are being broadcast into the mempool. So you need some policies to evict transactions from the mempool. Now there is a discrepancy between policies that help miners pick up transactions and their related ancestor and descendants, and policies that eventually lead to eviction of transactions. So miners typically order transaction by descending order ancestor field. So basically, what they do is that they pick up a transaction, add to calculate its period, then add to that to a transaction's fee rate, the fee rate of its unconfirmed ancestors. So they do this exercise. They sort the available transactions with them in descending order and then process it. So this is the miner's way of looking at transactions and their ancestors. Whereas the mempool's eviction policy looks at it, in a slightly different way. So transactions with the lowest descendant fee rates are evicted uh, from the mempool. So now there can be a case where a transaction and its ancestors uh, might have a low fee rate, total fee rate, but some of its descendants might uh, pay for them or RBF them to a higher fee rate. So if you look at a transaction, its ancestors and its descendants together as a package, there might be a case where this whole package pays more for the miner than just the transaction and its ancestor. So these kinds of these two policies are sort of contradictory, and they can lead to loss of a valuable transaction. Either the minor policy could drop a transaction, or the mempool eviction policy could drop a package of transaction that is actually valuable for a miner. So in order to address this sort of discrepancy between uh, uh, mempool and miner policy, cluster mempool designs have been introduced. So what this cluster mempool design will bring in is, um, it will help you improve fee collection by the miner, and it will help select optimal transaction for the block. Uh, uh, this problem of optimal selection becomes complex without the cluster design. In the existing case, it is very difficult to keep track of all incoming transactions, match them up with their ancestors and descendants, and sort the list, and keep updating the list as new transactions keep coming in. So it's a computationally expensive task. Um, Cluster mempool design will improve this computation task. So that is the idea or motivation behind this computation, this cluster mempool design. So the class. So now we'll have a look at the design of the cluster mempool. Uh, cluster mempools are a data structure or a design in Bitcoin Core, where the transactions are represented in a directed graph. So basically, the vertices in a graph are the transaction, and the edges are the spending relationships. Like the edges define which transactions ancestor and descendant. So in this diagram, you can see there are 4 transactions. If you from the vantage of transaction C, it has ancestors A and B, and it has a descendant D. So what this cluster mempool design does is that it groups these 4 related transactions as a cluster, and inside these 4 related transactions, you have different chunks. So A and B are direct ancestors to C, and they are classified as a chunk. C is a chunk by itself, and D is a chunk by itself. So this is the basic design of a cluster mempool. Having done this, we can like modularly remove or insert different chunks into this cluster. So this cluster's calculation or cluster structure is maintained, and you can atomically include or exclude different chunks from this cluster. So that is the idea behind this design. So, what is the implementation status of cluster mempools? Now they exist as 2 PRs. One is for the cluster data structure, as we described above, and another is for a class called Txgraph. So this Txgraph is the core data structure that underpins this cluster mempool design. Uh, so all these directed graph structures, nodes, and edges are all encapsulated in the Txgraph. So it provides high-level operations that you can perform on the cluster, such as clustering, chunking. You can perform fee rate analysis, create a list, sort the list, and all. So you can do all these high-level functions on the cluster mempool. So that is what this class is for. Now, 3 new functions have been added to this Txgraph class. That is all the change is about. So what 3 new functions that have been added? They have added a get main staging diagram. So what this function does is that it returns the divergence between main and staged fee rate diagrams. So basically, it shows how, like for example, in this cluster, if you are replacing this chunk with some other chunk, you can using this main staging diagram, you can get details about how this particular change that you are doing will affect clusters ordering and stuff. So you can do that with this function. The second function is that they have added as get block builder. So what it does is that it iterates through your graphs uh, uh, graphs chunks from highest to lowest fee rate for optimized block construction. So it can iterate through your graph and then sort it for optimized block construction. Then you have this get worst main chunk. So it sort of identifies the low fee rate chunk within the main diagram, uh, pinpointing which cluster subset should be evicted first. Like for example, if this particular chunk is the one that is paying the lowest fee rate, and if you evict this, the fee rate of the entire cluster would improve. In that kind of situation, this function can be used to iterate through all the chunks that is inside your cluster and identify which one pays the lowest fee rate. Probably you can evict this and put some other transaction into it. So these are the three different methods that have been added to the TX graph class. So these it is a work in progress, and hopefully this cluster mempool, when fully implemented and merged, will improve will improve or come in handy when there is a high fee environment and you have a lot of eviction problems. Uh, that sort of completes our look into the newsletter 355. I'll pause for a second and wait for some questions. Uh, cool. If there are no questions, I think we are done with today's session.